Je m'appelle Evgeny Mandrikov. Je suis un russe. Et je suis désolé. Je continue en anglais. Okay? Okay, so I'm one of developers and project leads of Java code coverage library named JaCoCo in my spare time, and of a plugin that is based on this library for Eclipse named Eclipse ECLEMMA. You can find me on Twitter, on GitHub, and so on. A little disclaimer, not in my spare time. I work for SonarSource company, which develops product SonarCube, SonarLint, and so on. If you want to know more about this, please come to our booth. Please participate in meet and greet. And whatever I'm going to say now, I'm going to say without my SonarSource hat. Before we start, let's try to avoid cliché. Is it a French word, right? OK, let's try to avoid cliché. Let's start from the questions. More seriously, questions from me. Who came here to learn more about how to compute code coverage, how to write good tests, and so on? OK. Sorry for you. This session is not going to be about that. Who came here to learn more about JaCoCo library? OK. Who already uses JaCoCo library? Wow, cool. Good for you. It's not going to be mainly about JaCoCo library. Who came here to learn more about Java? OK, not that much, but yeah, we're going to talk about Java, not about JavaScript, not about other fancy languages. We're going to talk about Java. More precisely, we are going to talk about code coverage mechanics, which tricks we do use to compute code coverage, how we compute code coverage, and so on. We're going to look deeper in the, let's say, JVM. And so here is a real disclaimer. I know you are tired. I know it has been a long day. It's the last sessions and so on. But please be ready for some bloods outside of JVM. We're going to speak strong language. We're going to look into bytecode. Be ready. Sorry for that. Sorry for intense violence of your brain. Yes, I will try to do this. And of course, we're going to look on implementation details. There is a dragons, be warned. Whatever I'm going to show you, use it on your risk or don't use it all. A bit of history about JaCoCo as a library. Initially, there was a library named EMMA, code coverage library. Unfortunately, let's say it's died a long time ago. Out of this EMMA library, there was Mark Hoffman built a plugin for Eclipse named ECLEMMA. At some moment of time, it became obvious that EMMA doesn't evolve while Java 7 was coming and so on. And there was a need to develop a new library. So JaCoCo was born out of ideas of original EMMA library with all the experience of developing plugin for Eclipse. And in Eclipse plugin version 2, JaCoCo became a default code coverage engine. Funny fact, even this initial library EMMA was developed to measure code coverage by tests. There were exactly 0 tests. OK, what happens nowadays? Nowadays, Java 9 is coming, and we will try to provide support for Java 9 from a day 0. Actually, we already support Java 9. You can take latest release of JaCoCo and latest early access build of JDK 9, and it's just going to work. Also, nowadays, we are trying to migrate ECLEMMA project into Eclipse Foundation so that it will be available for you out of the box with the next release of Eclipse, which is Oxygen. Because we believe that code coverage measurement is needed for you as an Oxygen. OK? OK, let's move on. Before we look into internals of implementation, I'd like to refer to a fact called observer effect. There is a pretty long statement, but the main part of it is that any instrumentation, any measurement is going to alter the state of what it measures. And code coverage is a measurement. Code coverage is a measurement of execution. So in any case, it's going to alter the state of your program. And the goal of any code coverage tool is to minimize this effect, to minimize impact on performance, to minimize impact on performance, and to not have any impact on an actual result of your application, to not change the way your application behaves except a little overhead of performance. So how are we going to do this? There might be different approaches. We could do some runtime profiling, but this is not the way how we do it. We do bytecode instrumentation. Of course, there is also source code instrumentation. You might know Atlassian Clover tool. It does source code instrumentation, modifying your source code, and then process of compilation again, and only then you're going to get your measurement. This is pretty tedious to do within your build process because you need to recompile your sources again and again. So we don't believe in this approach. We do believe in bytecode instrumentation, and there is two ways. Either we take already compiled classes and we can modify them on a disk, and then we run them, and this is called offline instrumentation, pre-instrumentation, which you do before running your application. Or thanks to the existence of Java agents starting from Java 5, we can do this on the fly. Oops, sorry. Yeah, let's move on. And so JaCoCo works on class files only. It doesn't need your source code. It can work even without the source code. You have just some jars from somewhere. You can execute them, and you can measure code coverage. The only problem, you won't get a fancy result which will show you align numbers because you don't have a source code. But you will have some measurement, at least on a class and methods level, because they do present it in class files. So how it works overall. You have a class file, you do instrumentation, either pre-instrumentation, either on the fly. Then you execute what you just instrumented. You receive execution dump in some internal format. Then to get a report, you again take your original class files, you take execution dump, you perform the analysis, and analysis gives you a report. Pretty simple. As easy as just setting an argument for the JVM. You provide a Java agent, and everything going to happen on the fly. Again, thanks to the ability to write so-called agents that able to hook into the process of JVM of loading and transforming classes. So on the fly, you can register your transformer, which will modify bytecode of what was just been loaded. As modification of bytecode is quite tricky, complex, and so on, we have some validation test suites. This is example how it looks. We annotate some source code with line information, and then we have assertions, what we expect to be covered, how many times executed, and so on. And we do test on 5 major JDK versions to guarantee that it works and doesn't break with new releases. Yeah, and of course we test on JDK 9. And thanks to this allows to find not only issues in JaCoCo, we find a pretty good amount of issues in JDK. Some of them resolved, some of them not yet, planned to be resolved, and so on. Apparently, we are within 5 top contributors of issues into OpenJDK among open source projects, along with IntelliJ IDEA and Apache Tomcat and so on. But OK, instrumentation. So we're going to modify bytecode. Bytecode is a sequence of some instructions, and we need to insert in certain places our own code, which will allow to measure what has been just executed. There is not that much positions where we need to do this. If we have a return from a method, we can just insert so-called prop just before return, and voila, we know that we reached this return point. If we have some goto, yes, again, funny fact, even though Java has no goto, on a bytecode level you have a goto. So if we have a goto in a bytecode, we can just insert prop before goto, and we know the fact that we reached this point, and there is a jump from 1 position in bytecode to some other position. If we have some condition, then we do a little trick just for simplicity of our analysis. We invert the condition, insert a probe, and insert jump. This allows us to record the following fact. If original condition was true, then then we should jump to the target, and so then our probe will be executed. And finally, if we have some sequence of instructions, we can insert just somewhere in the middle probe, and this probe will say that everything what comes before, also all the instructions before the probe were executed. These four strategies allow us to record execution of any complex control flow. Pretty simple so far, right? I hope so. Okay, let's move on. We already said that we should minimize impact on the performance. So let's see how we can do this. So what are the requirements for a probe? Requirements for a probe is the minimal runtime overhead. We want to minimize this. We don't want to have any side effects on execution of application. We don't want to alter the state or result of execution of your application. As a kind of consequence and so on, what we insert should be thread safe. Otherwise, your application was thread safe. We insert something non-thread safe. Your application is not thread safe. Not so good. Also not good if your tests are executed in parallel and so on and so on. The result of computation of code coverage might be incorrect. So we want to insert something which is thread safe. Obviously, what we insert should actually record the fact that something was executed. Otherwise, why we would insert it? And we need to be able to map it back to initial position in the class files in order to construct a report at the end. So we need some way of identification. Apparently, it turns out that simplest construction which satisfies all those conditions is just assignment of true to the Boolean array. That's it. It gives us following bytecode that we need to insert from something like, if I'm not wrong, from 4 to 7 bytes we need to insert as a prop. Why thread safe? Just because we always write the same value, we never read back. Why identification? Because props, we can numerate them sequentially, so we can identify them back. Minimal runtime overhead, okay, pretty hard to prove, but try to find something faster. Okay. No side effects. You know, okay, we will talk afterwards. For sure, we will talk. No side effects on application code because so far we touch only our array. That's it. The good question here is, okay, this array we can put it somehow in a class, but how it will appear in this class? From where? And how we will take the data that we recorded at the end, how we will take it back? So runtime access to the runtime of JaCoCo that orchestrates creation of a dump file and so on. This is what we are going to look on soon. Before that, let's have a look on bytecode of assertions. So you have pretty simple class fun, with the method fun, which just does assertion. How bytecode of this looks like? To answer on this question, we can use standard JDK tool JavaP. We can ask it to, let's say, decompile our class and show us a bytecode. And we will see something crazy like this. First question that can come to your mind, what the hell is get static assertions disabled? Get static is an instruction which reads a value of a static field. But we don't have in the original class any static fields. What is that? Okay. No one knows? Apparently, Java compiler, when processing such a class and generates a class file, bytecode for it, apparently it declares a special static field called Assertions disable with initializer that goes into the class and calls a method there, which is called desired assertion status, which at the end is going to give you back whether assertions enable it or not for your class. And this is an optimization trick, because if you will be asking a status of assertions, whether they are enabled or disabled each time we need to do an assertion, this will probably be a good hit for performance. So the trick is to cache the value into some static final field, and so you don't need to constantly ask some complex runtime to give you an answer. Also, you might notice, and this is quite important, this field is marked synthetic, a special attribute which denotes constructions that are not presented in source code, but that are presented in a bytecode that were generated by a compiler. So such a synthetic field was generated. Pretty nice trick, and why? Because it's a nice idea. We can use it for our own needs. We can avoid a cost of going to the JaCoCo runtime by injecting also some static final synthetic field, which will hold exactly this array of props. Smart, isn't it? I hope so. Okay. Let's move on. Do you know some other examples of synthetic constructions that are injected in your bytecode? Any ideas? Yeah, okay, let me give you a hint, not for you, for everybody else. Let me give you a hint. Such a program, there is an inner class, there is an outer class. Inner class accesses a private field of an outer class. Apparently, while this is allowed by Java language specification, this is against Java virtual machine specification. Java virtual machine can't give you an access to a class within the same package, to the field of another class within the same package if it is private. So, and this is called bridge method. Compiler generates a special synthetic methods that are not private within package, which are package local, which have a crazy names. And those fields actually manipulate on a field so that classes within the same package can have an actual access to the private fields. Okay. Let's move on. Maybe some other examples of something generated by a compiler. No, this is actually wrong. It's a common misbelief that two methods that compiler injects into enums, values and value of, they are synthetic. They are not. And I suppose the main reason for this is those methods should be visible by IDs. And normally IDs, they would skip all the synthetic methods because you don't want after completion of bridge methods. You don't want after completion of desired assertion status. You don't want to see this. So they hide all the synthetics methods. But you want to have an access to enum methods. And that's why even those that are generated by compiler, they are not synthetic. Why this matters for code coverage tool? Because it's pretty much the same story. You need to filter some code because it's not relevant for a measurement of coverage. You don't need to measure something that was generated. You're just going to trust the generator. So by default, we exclude all the synthetic methods. And this means that we don't exclude values and value of methods. Till the previous week, there was pretty popular ticket to exclude them. Previous week, we finally excluded those two methods. Let's move on. Some other examples of synthetic constructions. If you have a lambda in your source code, actually, the body of a lambda will be stored in a special synthetic method whose name starts from lambda $, blah, 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 something. You can verify this, yeah. You can see, again, using Java P, you can ask to print line numbers, not just decompile and not just print you a private members of your class. You can ask line numbers, and you will see that line numbers within this method, they correspond to the line numbers of your Lambda. Why this is important, again, for a code coverage tool? Even though we should exclude synthetic methods, we shouldn't exclude lambdas. Otherwise, you wouldn't have any coverage within your lambdas. And again, this is a pure implementation details because nowhere, nor in Java language specification, nor in virtual machine specification, nowhere is said that lambdas are going to be translated into such methods. They are not guaranteed to lie within the same class, actually. They can be somewhere outside. This just was convenient to put them into the same class and some synthetic methods. Okay. And as we operate with bytecode, we use pretty good, not pretty good, awesome library ISM. And there is some difficulties with that because if we take latest JDK, we will take Java version 9 that is not yet released, that is early access. We can compile it, but if we will give bytecode that we just received to ISM, we are going to get illegal argument exception. ISM is not yet compatible with Java 9 bytecode. It will be, but this is a chicken and an egg problem because we can't get a library before the specification is frozen. Specification is not going to be frozen till the release of reference implementation. So what to do? Funny fact here is that if we will take quite old standard Java decompiler from a previous version of JDK, it will happily read exactly the same class file, as long as this class file doesn't use constructions that are not understandable. Another interesting fact and a hidden treasure of this JDK decompiler is that you can actually annotate bytecode with the source code at the same time, giving some tricky options on the command line. But OK, let's come back to a problem. How we can solve this illegal argument exception? We can do a clever trick. We can see if this is a newer bytecode. If it is, let's pretend that it is not. Let's pretend that it is bytecode of Java 8. There is no new instructions added into the bytecode. Only things that were added is constant pull attributes for module info, so for modularity support. But we are not going to touch this information. We are not going to manipulate with modulus. So we can safely downgrade the bytecode. Once we're done, we can upgrade it back to the 9 version, and no one outside of our code coverage tool is going to see that we did this trick. This is how we avoid this illegal argument exception problem. This is almost the only one thing that we needed to do to support Java 9, almost. But OK, let's move on. I hope your brain now is warmed up enough. OK, let's move to the really hardcore things. Let's come back to our assertions. So let's say we again have a super complex method which does one assertion, is 1 equal to 2. And we have it within a class child, and child should extend some parent, so we have also some base class. And the base class looks like this. We have a static initializer. For some reason in our static initializer, we do want to instantiate our child and call on it some method. And of course, we want to execute such a beautiful application. OK, I see. Your brain starts working. OK. So yes, question is, what is going to happen? Let's say I enable assertions and I start this application. What's going to happen? What are the options? Sorry? Class not found. No, we have child, we have base. No, not class not found. Assertion exception, okay, why 1 not equal to 2? Assertion exception, pretty obvious, pretty logical. What if I disable assertions? In a command line, I can say Java minus disable assertions, da-da-da. Assertion exception. What? Exactly, what? Why? If you will recall how assertions implemented, you have a static final field initialized with some value. And the name of this field is assertions disabled. So once this field is initialized, you will know whether assertions disabled or not. But before this field is initialized, there is some default value. And default value for booleans in Java, false. Depending on the order of initialization, if you called before this field initialized and you look into this field, you're going to see the false. So what happens here is initialization of child triggers initialization of base. Field in child has a value false. During initialization of base, we already call a method, and bam, we get assertion error before we initialize the field. Such a problem we call a bad cycle. This is really bad. Don't do like this. If you do this, you can even step on class loading deadlocks. But okay, that's another story. Why this is bad for our code coverage tool? Because we use exactly the same trick. When the field is not initialized and we are on the same bad cycle, we are going to get a null pointer exception. Field is not initialized, it has a null as a value. This is a problem. And if I'm not mistaken, in Cobertura, which is another code coverage tool, in Backtracker, there is a report exactly about this. Because apparently some people, they do such crazy bad cycles. How we can solve this? Okay, we can introduce another synthetic method that will be doing initialization for us and in a clever way. If it is null, then we need to initialize. Once we initialize it, we can return the value. And let's just call this method each time we need to get a probe array. That's it. And now you get an answer on a pretty common question why JaCoCo injects two synthetic constructions. One is a field, another is method. One because we want to give you a speed, because we want fast access to the probe array, to the coverage data. Another one is to avoid bad cycles problem. And unfortunately, some libraries that use reflections, that they assume that there is only fields that are presented in source code. They don't exclude synthetic constructions, and this is a pretty common problem. I run my application without code coverage, it works. I run it with code coverage, it fails because of reflection and something like this. But okay, let's move on. Let me pose a question. Is there any problem with this code? Hopefully there is a branch prediction, there is inlining, so after some time. But okay, we can talk about performance a bit later. Some other ideas? No, we don't allocate. We go to the runtime and ask runtime to give us array, and at the time of access, runtime has a synchronization, so there is only one allocation. No, once again, we go to the runtime, runtime has a synchronization at It's not a multi-threading issue. Again, we go to the runtime, runtime has a synchronization. But okay, let's don't waste time, let's move on. If you will read Java Virtual Machine Specification, our Bible, one of, exactly chapter about put static, and here we have a static field. So we do use put static bytecode instruction. If you will read a pretty long paragraph here, we will find words that say, if field is final, then put static instruction must occur in so-called CLInit method. Otherwise, illegal access error is thrown. CLInit method is a static initializer of a class. So let's have a look on our example back. We have a static final field which is initialized outside of static initializer. And this has been working for more than 6 years for sure. How hell is it possible? It's possible simple like that. It was not checked by the JVM. It is checked only in JVM version 9, starting from some build, and only for class files of a specific version. So we started to fail just recently, just a couple of months ago. OK, let's solve this problem. How we can solve it? OK, let's remove final. That's it. OK. Now, why are you laughing? This is truth. We just removed the final. But indeed, that's not the end of the story. There is also interfaces. And in interfaces, any field in interface should be static final. We can't remove final here. OK, it is not a problem. Our interfaces, they contain only declarations of a method. They don't contain executable code, so we don't need probe array here. We are not going to execute anything unless we have a default methods. Yeah. OK. But OK, in fact, before solving this problem, we need to answer on the question, is there a problem? If bad cycles can't happen with interfaces, then there is no problem. We can keep it static final, we can initialize it in static initializer, and that's it. We don't need any trick with additional method which will be doing initialization. So before solving a problem, we need to confirm that there is a problem. Let's try to construct bad cycles with interfaces. To do that, we're going to come and read our second Bible, Java language specification. When initialization occurs, there is again a lot of text, but it boils down to the following. Class is initialized immediately before instance of a class is created, or static method declared by a class is invoked. Pretty simple. Okay? When class is initialized, then all super interfaces that declare any default methods also initialized. Simple, I hope. Okay, let's move on. So we will have some class. We will initialize it, which is supposed to trigger initialization of super interfaces that contain default methods. Or, OK, we can call a static method on this class. Then we're going to have some base interface. In order to trigger initialization, we're going to have default method in it. And again, to trigger a problem of bad cycles, we are going to create instance of a child. And on a child, we are going to call some method. OK? Now, child extends base. We want to trigger the problem. We're going to have this method that we are calling. We can, because we can just make it default. Just to see the order of execution, who calls whom, it's pretty natural to use throw statement to throw some exception, and you will see the stack trace. And to see again that initialization of child happened, we will have a system out, println, and so on. Any ideas now what is going to happen if you run this? Sorry? Yeah, it compiles. It's OK. Sanity check passed. But OK, what are the options? It's going to crash. Who thinks that it's going to crash? No one. OK. One. OK. Who thinks that there will be, again, demonstration of bad cycle problem? The method is going to be called before initialization of child happened. who thinks for this order? 1. Who thinks that the order will be, let's say, opposite correct? Initialization happens after? 1. Others? There is not, I don't know. That's pretty smart answer. Actual answer, it depends. Okay? So if you run this, I executed this at home, and I got following order. I came to work, I got another order. Why? Because a version of JVM was different. Before update 40, you're going to see the orders at, again, bad cycle. After, you're going to see a good order. Okay? But that's not the end of the story. We will also see a crash because we are throwing some exception. So you was right. If you don't have a throw statement, then we're going to see a correct order. We also can verify a case of a calling of a static method, and bam, order again incorrect. What a beautiful world. Why? Because it is a bug. We reported all them back, and finally in update 152, we're going to get correct order for all of them. But because of existence of all this mess in previous updates, we will need to solve the problem. We confirmed that the problem exists. Before the full initialization, someone can call the method. So we have no choice. We need to, in interfaces, we need to mark field as final, and unfortunately, for interfaces, we will have a slow pass. If the value is not initialized, then we will just ask the runtime and return the value. Let's have a little rest. Your brain is warmed up completely. Look at this picture. It represents a jar hell. Why? Because there might be a lot of different classes, and actually classes with the same name, they don't necessarily represent the same bytecode instructions. They could come from different classes, from different class loaders, from different jars. So in code coverage library, we need to solve the problem of a class identification, how to associate what we just measured back to some report about some class. To do so, we do a simple CRC64, and this is so-called class ID. And this is, again, a common problem with usage of JaCoCo. If CRC doesn't match, if you somehow on the way from measurement back to the way to generate report, code coverage report, you modified your bytes, your bytecode, we wouldn't be able to map code coverage data back to generate a precise report, just because we don't know to which class file this data belongs. Okay, another problem. Again, in a world of jar hell, we can have class loaders. Class loaders, we can implement them. In OSGi, we have tons of class loaders that allow you access to some things, that disallow you access to some other things. So, for example, we can have such a restrictive class loader that disallows us access to almost anything that lies outside of a Java package. And then a question, how hell we are going to call some runtime to get an actual instance of this prop array instantiated by this runtime? We can't actually use anything outside of Java package. And our JaCoCo runtime is obviously in JaCoCo package. We were so close to implement our library, but we failed. No. Thankfully, there is a solution. We have an agent that can modify almost anything within our JVM. And so what we do, we simply modify some rarely used class to inject a special field in it. And this field will give us access to our runtime. I never said this to you, OK? But OK, what we need to pass to runtime? We need to pass our class ID to be able to identify it back during a report generation. We need to send a name of a class which we're measuring, and we need to ask to allocate an array of a certain size. We need to to say, okay, give me this amount of props. Again, in Java package, there is no interface that would describe what we want to pass. So we need to use something which is available in Java package. So let's pass, okay, arguments as an array of object. I know there is a boxing, we might get some hit on performance, but we have no choice. So let's do this, and let's use equals method to call runtime, just because equals is always available. How we gonna get back array? No, we already called a method. The result of calling this method should return us array. Equals returns a boolean, not array. No, thankfully, arrays in Java are mutable. We can get it back just in array that we send it just now. And that's a trick how we can bypass boundaries of class loaders, boundaries of OSGi, boundaries of modularity system. We don't do clever tricks, we use standard Java method calls. Okay, at the end, please get involved, have some fun. Please test JDK 9, see how your application works with it, see how your library behaves with it. Feel free to jump into discussions on our forum about JaCoCo. Feel free to answer questions now that you know some internals. Feel free to help us with development of both Eclipse plugin and JaCoCo library. And enjoy. If you have questions, we still have 3 minutes, so.
How do we cope with libraries, test libraries like Boa Mockito? Change the bytecode.
Yeah, the question is how we deal with such libraries as Power Mockito that change bytecode. This is a very good question, and actually, I had some backup plan. But okay, indeed, there is a problem with interoperability with Power Mockito. Recently, they fixed some problem, and the problem was Power Mockito was always ignoring JaCoCo initialization synthetic method. They fixed this. So nowadays, if you don't use on-the-fly instrumentation with agent, you will get JaCoCo working just fine with Power Mock, because JaCoCo is going to see class before Power Mock modifications, is going to record checksum of this class, then Power Mock going to instrument this class, and then we're going to build a report back on not modified version. This doesn't work with an agent, and this doesn't work with an agent not because Power Mock modifies bytecode, but because actually Power Mock bypasses agent. Power Mock always goes on a disk and reads a bytecode from a disk. So somehow it's not a problem of JaCoCo. Power Mock wouldn't work with any kind of an agent. But okay, good news for you is that we are in a contact with current maintainer of Power Mock to see how we can proceed with this issue. Some other questions?
In your last example, with the runtime problem, what happens if the class you modify it's used in the jar?
It depends. But okay, question is, in the last example, in order to get an access to the runtime, we modify some standard class, and what if this class is actually used? It indeed depends, because if it is used and it is loaded after our modification, it's okay. No one looks into a synthetic fields of this class, and no one will ever notice that we injected fields there. If this class is used on a startup sequence of JVM before our agent starts, we have a problem, because we can't anymore retransform this class. It will fail with I don't remember, schema modification exception or something like this. So, so far, we don't know examples whether when this class is used so early on a JVM startup sequence before our agent. So far, we are safe. If this ever happens, we're going to find another class. And I think time is over. Thank you.